Welcome to video 45 in our series on tensor calculus. In this video, we'll introduce a very useful determinant tool known as the delta system. Let's begin by defining this new expression as the determinant of these individual Kronecker delta terms like this. Now, if we do that, we can expand our determinant to look like this. And you'll remember that we do this by taking these three factors and forming this term. We take these three to form this term, these three to form this term, and then we take these three for the first negative term, these three for this one, and these three for the last one. Okay, so let's see if we can make sense about how to evaluate this new expression. The first thing we'll say is this, that the only way that any of these terms can be non-zero is if all three of the factors are equal to 1. And those three factors will be equal to 1 only if the two indexes on each Kronecker delta factor are equal respectively. Now what that means is that it's impossible for any of these terms to be equal to something other than 0 unless I, j, and k are the same combination of values, the same set of values. Because if they're not the same set of values, then we're not going to be able to create matching pairs of these index values on any one of these six terms. For example, if we had I, j, and k were 1, 1, 2, and r, s, and t were 3, 2, and 1, well, there's no way that we can set indexes I, j, and k equal to these values on any term and then match them up with these in the bottom, no matter how we rearrange the order of these expressions. So the first point is this. For any of these terms to be non-zero, the set of values, the combination of index values for I, j, and k must be the same combination of values for r, s, and t. Okay, the next thing is, let's look at what happens if we have duplicates. Let's say that I and j are equal. So we're dealing with 1, 1, 2. And of course, we'd have to have the same values in the set for r, s, and t, but for now that doesn't matter. Let's take a look at how this works. If we say that I and j are equal, then that means that I and j are equal here. They're also equal, let's see where this would be, k, t over here. If they're equal here, then we can swap these two terms, and you find that this value is exactly the same as this one. One's positive, the other's negative, so these two will cancel out. Likewise, when I and j are the same here, then this term will cancel out with this one. And when I and j are the same here, then these two terms will cancel out. So if I and j are equal, then these are going to cancel each other out in pairs. The same thing happens if we, well, let's pick j and k. Let's say we had 1, 2, and 2, where j and k are equal. If j and k are equal, then let's see, we're going to have this term is equal to this one. And then j and k are equal here, then this term is going to equal that one. And j and k are equal here, and this equals this. So you can see that it also works if you swap, if you have a duplicate from between I and j here. So anytime we have a duplicate value in here, it's impossible for this expression to be anything except 0. So that leads us to understand that these must be unique values. They must be distinct values, and the set of values must be the same. Now, working in a three-dimensional space, which is what we're doing here, means that I, j, and k must be some permutation of the numbers 1, 2, and 3. Likewise, RS and T must be some permutation of the values 1, 2, and 3. So the only difference is how we rearrange these and what order we put them. Well, look at it. Let's just take this as an example where I equals R, J equals S, and K equals T. Well, if you look at it, this term would equal positive 1 because I equals R, J equals S, K equals T. But that's the only term for which that's true. All the others are equal to 0. So when this is the case, then the expression evaluates to positive 1. Well, let's take another example. Let's say I, J, and K are 1, 2, and 3, and R, S, and T are 2, 1, and 3. Well, in this case, I is equal to S, J is equal to R. So that would be I equals S, J is equal to R would be this term. Oh, sorry, it would be this term. So I equals S, J equals R. Then because all of these values are 1, multiplied together they give us 1, and there's a negative sign, then the expression evaluates to negative 1 because all the others are 0. Okay, one more example. Let's say that I, J, and K are 1, 2, and 3, and R, S, and T are 3, 1, and 2. That means that I is equal to S, J is equal to T, and K is equal to R, and that looks like it would be this term. So this one is positive 1, everything else is 0, and the whole expression evaluates to positive 1. Now, notice in this last example, I'll put the other one up too. We had 1, 2, 3, and 2, 1, 3. We were able to change 1, 2, 3 into 2, 1, 3 just by swapping these two indexes. So there's a single flipping operation to go from here to here. And when we did that, we found that the result was negative 1. It's evaluated to negative 1. Well, here, we can't flip once to get here. We've got to first of all flip, say, 1 and 3 to get 3, 2, 1, and then we flip 2 and 1 to get this. So it takes 2 flipping operations to go from here to here, or an even number. So here's what we can say, that whenever the indexes are related, the permutations of the indexes are related by an odd number of operations, then the value is going to be negative 1. If they're related by an even number of flipping operations, then the value is going to be positive 1. So we can summarize all of that in words. We can describe it like this. We say that, first of all, if the upper and lower indexes are identical sets or combinations of distinct values, so in this case it means they have to be 1, 2, and 3. If that's true, then our expression is going to evaluate to either plus 1 or negative 1, depending on whether the upper and lower indexes are related by an even permutation or an odd permutation. And then the value of our new expression is going to be 0 for everything else. These are the only cases where they will evaluate to something other than 0, and it'll be either positive 1 or negative 1. Okay, now what we're doing here is actually defining a group of new expressions, or a family of expressions. So let's put up the next one. Here we have what our expression would look like if we're using only 2 indexes. And it's the same pattern. If we're using 2 indexes, then we say that this expression right here is going to be equal to the determinant of a 2 by 2 matrix using the Kronecker deltas. And of course, that's just this product minus this product, and that's how we get this. Well, notice that everything we've said down here applies equally well up here. if the upper and lower indexes are identical sets of distinct values, then that means it has to be the same combination. This has got to be the same combination as this, or neither of these two terms can be anything but 0. Likewise, if that's true, if they're duplicates, then the two are simply going to cancel each other out, so they've got to be distinct. And then if the relationship is an even relationship, then this is going to be the positive term. If it's an odd relationship, then this is going to be the non-zero term. So this whole description down here applies just as well to this new definition as the old one. Let's try a couple of things here. What would delta 1121 be? Well, it's got to be 0 because we have a duplicate here. What about delta 2312? That's got to be 0 because they're not the same set of indexes. What about delta 2332? Well, they're the same set of indexes, they're unique, and they're in an odd permutation relationship, so this is going to be equal to -1. So you can see how this description tells us exactly how to evaluate this expression. And by the way, let me point out that we can even apply this definition to our Kronecker delta ij. Of course, we know how this works. It's equal to 1 if I is equal to j. But notice how the same description works equally well even for this expression. Because if the upper and lower indexes are identical and distinct, well, of course they're going to be distinct. But if they're identical, that means that I is the same as j. All right, well, then if they're related as an even permutation, well, they have to be because there's only one order. So delta 1, 1, I can't reorder either term. So it could be 1 if the two are equal, and it's 0 if it's anything else. All right, let me point out a few properties of these expressions. First one would be this, that both of these expressions are tensors. And we know they're tensors because we know that the individual factors of the Kronecker deltas are tensors. So when we multiply tensors together, we get a tensor. And that's true for all of these. And then when we add these expressions together, the sum of tensors is a tensor. So that leads us to understand that this is a tensor. Same reasoning applies right here. Both of these are tensors. Now, secondly, they both possess the metronylic property. The covariant derivative, for example, with respect to m of delta ijk rst is going to be equal to 0. Well, how do we know that? Well, if we're going to take the covariant derivative of this expression, we have to take the covariant derivative of each term separately. And for each term, we'll use the product rule. So we would have the covariant derivative of delta I r times delta js delta kt plus delta I r times covariant derivative of delta js, etc., etc. And so what that tells us is that each of these factors we know to be 0 because the individual Kronecker delta possesses the metronylic property. So as we work our way through the product rule on each of these terms, each one of these expanded terms is going to have a factor of 0, and that's true for all of these. So that leads us to understand that this is true. Same reasoning applies here. The covariant derivative of this expression is going to be 0. So we need to add both of these expressions to our list of objects that possess the metronylic property, this one and this one, as well as our Kronecker delta ij, which we analyzed in a previous video. Now there are some important identities that I need to show you. Let's look first of all at delta I J K R S K. What we're doing is forming a contraction with this last index. Now to see what this looks like, let's just label this as K, and we have to put K on each of the places where we have T here. Let's see what that does for us. Okay, first of all, Kronecker delta KK is just 3. So you've seen that before. When we contract an index with itself on the Kronecker delta, it's going to be 3. So that's 3 times the other factors of delta I R delta JS. The second term, this index will will be absorbed because it's a dummy index here. So that's going to leave us just with the first term, delta IS, and this will become delta JR. All right, there's a contraction here and here. So that's going to be delta IS and the other factor of delta JR. And then in the bottom, we'll have the contraction here. That's going to be negative delta IR. And the other factor is delta JS. And this term, this contracts, gives us a negative delta IR delta JS. And the last, again, this is a factor of 3, so we're going to have negative 3 delta IS delta JR. Okay, now we can combine some terms. So here we've got this guy is the same term as this one and this one. So combining them, we're just going to have delta IR delta JS. And the same kind of thing happens right here. This combines with these to give us a negative delta IS delta JR. And you will notice that what we wind up with is exactly this. In other words, this expression, this contraction, is equal to delta IJRS. All right, let's do the same thing now by forming a contraction right here. Let's make S a J like this and this. So we're going to find out what delta IJRJ looks like. Okay, well here we have this again is a factor of 3. Delta JJ is 3, so we have 3 delta IR. In the second term, the J index is absorbed, leaving us just with delta IR. And that equates then to 2 times delta IR. And finally, you already know that the contraction of the Kronecker delta with itself is just equal to 3. So let me summarize all of these important properties this way. And we'll conclude with one final relationship, and it's just this, that our new expression delta IJK RST is the equivalent of E IJK in the upper position times E RST in the lower position. Now, this is pretty easy to see because you know that this permutation symbol is going to be 0 unless the indexes are 1, 2, and 3. Same is true here, 2 and 3. And then you know that the value of this expression is going to be a positive 1 if this is an even permutation. So let's say they're both even permutations and they'll both be plus 1. If they're both odd permutations, it'll be plus 1. And if one is even and the other is odd, then the product is going to be negative 1. So this product will be plus 1, negative 1, or 0 under the same conditions that we described a moment ago for the evaluation of this expression. Now many authors will actually define our new expression here using this relationship. And then once they've done that, they can derive this expression and all of the other properties that we evaluated earlier. The fact is that the two are absolutely equivalent to each other, so you can use either one as the primary concept and then derive the other as a result. Okay, that's quite a bit to take in, so let's conclude the video here and go do a quick recap. In this video, we defined the delta system as you see here. We said that the delta element with 3 indexes, upper lower, is the determinant value of a 3 by 3 matrix with the individual Kronecker delta symbols you see there. Likewise, the delta system with the 2 indexes, upper and lower, is defined as the determinant of a 2 by 2 matrix like this. Now, by doing this and expanding it out, we were able to quickly prove that each of these new elements are tensors. We were also able to show that they possess the metronylic property. Now, after considerable analysis, we were able to determine how to evaluate these expressions according to these very concise rules. This description describes how each of these things are properly evaluated. We discovered that if the upper and lower indexes are identical and distinct, meaning if we had 1, 2, 3 and 1, 2, 3, for example, we can't have any duplicates either in the upper or lower position. That is the distinct portion of this. And the second is that the indexes have to be identical sets. For example, if I and j are 1, 2, and r and s are 2 and 3, then this condition is not met because they're not identical sets. They're distinct, but not identical. So if they are identical sets of distinct values, then the delta value is going to evaluate to either plus 1 or negative 1 depending on the order. And if the order is such that both the upper and lower indexes are even permutations or odd permutations, then the value is going to be plus 1. If the order is such that one is an even permutation, the other is an odd permutation, then the value is going to be negative 1. Now, the value of our delta symbol here is going to be 0 in every other case. In other words, if there are any duplicates in the set of indexes I, j, and k, or duplicates in the set RST, or if the two sets are not identical, as we pointed out before, then the value is going to evaluate to 0. And that common description works for all of the delta symbols that we define, no matter how many indexes there are in the upper and lower positions. Okay, with that we went on to derive a few identities. So let's look at those real quick. We were able to show that when we contract one of the indexes, like k here, 3 indexes upper and lower, and we contract one of them, it's equal to the delta element with 2 indexes upper and lower. If we contract one of the indexes on a 2 by 2 delta system, then it's equal to twice the single Kronecker delta. And when we contract the Kronecker delta itself, we just get the value of 3. It's an interesting pattern. It simply goes from 1 to 2 to 3, and each one relates to the next delta symbol in this fashion. And finally, we said that the delta system could also be defined this way, that it's exactly equivalent to pairing up two permutation symbols in this way, that the description of behavior that we have up here is exactly the same behavior that you'll find with this product of permutation symbols. And so the definition we introduced with the determinant values above is exactly equivalent to this. In fact, many authors use this as the definition and derive the other properties from it. So you can use either as the basis for the definition and derive the other properties as a result.